And
AC equals negative alpha R parallel to surface.
okay, so as long as you use a coordinate system like this, and we define omega and alpha as positive if they're counterclockwise, then the velocity of the center is equal to negative omega r 0, 0. Yes. And the acceleration of the center is negative alpha r 0, 0. And it's always easiest to do these problems with the y-axis pointing out of the surface. So if it's rolling up a wall, you have to have the y-axis horizontal. Omega, yep.
If either of those were in the opposite direction, that would just work out in the sign.
Right. Yep. I mean, just so think about the directions, you know, and that it makes sense. Like right now, if omega is positive, you have a velocity in the negative x direction, and you know that if a wheel's rolling this way, it has to be going that way. So if you just think about it intuitively, you can figure out the sign thing. Any other homework questions? Yes. Mm-hmm. What does it ask? Oh, okay. No, you don't have to remember that. I don't think I've ever put that on a test for one thing, but if I did put it on a test, I'd give you that equation. And if I didn't give you that equation, you could ask for it and I'd write it on the board. Then you could email me, have the person who is proctoring it, have them send me an email and I'll send it to them. Yeah.
We take into consideration the centrifugal acceleration of points to the center, but not the center to the ground. The only
Okay. Yeah, so if you're trying to calculate the, so I'm going to call this point B, that's the contact point. The center is C, and opposite the bottom is the top T. And if you're trying to calculate the acceleration of the top, that's the acceleration of the top relative to the ground. And that's equal to the acceleration of the top relative to the center plus the acceleration of the center relative to the ground. You don't have to ignore anything here. There's no centripetal acceleration to this at all. You know, this acceleration is just negative alpha r 0, 0. And then this one is a circular motion thing. So here you have to use alpha cross r plus omega cross r. Watermelon. So it's not like you're ignoring the centripetal acceleration here. We showed in that whole derivation that there is no. Not for the center. I think I started to write that down and then erased it. So you might want to check your notes on that if it still says it. But we know that, I mean, just by like sort of inspection of what's going on, you know that the center of a wheel, of a round wheel, isn't going anywhere. So it can't have any velocity and it can't have any acceleration. I mean, up and down it can't. So So this is the full acceleration of the center, and you're just adding the full accelerations together. Yes. Oh yeah. So if you wanted to then express, so you get some answer here. I'll call this the acceleration of t relative to a rotated coordinate system. You know, expressed in a rotated coordinate system. One thing you could do is just take the projections onto your new x and new y axis. So you won't have to do this on the test. So maybe that's the only answer you need. But there's two ways. But there's two ways to express it in a new coordinate system. The first is to 1 by 1 use the dot product to find the projections onto the new axes. So the way you would do that is if the new x-axis is, well, let's do it for a 20-degree angle. So like do it for this case. Let's say this is 20 degrees. So there's two ways to express in a new coordinate system. And the new coordinate system that I'm going to use is this one in this case. The first one is express the new axes in the old coordinate system and use the dot product to find the projections. Okay, so the new x-axis so if we want to express this vector, now that x-axis is just a unit vector, and we want to express that unit vector in this coordinate system, that's going to be cosine of 20 sine of negative 20, or cosine and sine of negative 20. So we take the, who's with me on that? Okay, good, two of you. Perfect.
So you're going from the standard to the...
You're just expressing, so yeah. No, we're going from, so it was easy to do the calculation in this coordinate system. So we have a vector in this one, and now say you want to, like, people don't want it in this wacky coordinate system, they want it in this one. So you want to, so express this unit vector in your coordinate system, and you get, so the new x-axis is 0.940 negative 0.342. That's cosine and sine of negative 20.
So those are like, to me, that's values for what we got.
No, that is the cosine and sine of negative 20. So that is the new x-axis expressed in that old coordinate system. So this is the new x expressed in the old coordinate system. And so then the x component in the new coordinate system is just the vector we had. That's the acceleration of the top in the old coordinate system. This is vector dotted with 0.940, negative 0.342. And then the new y expressed in the old coordinate system. So how would you represent this vector in this coordinate system? It would have an x component of positive 0.342 and a y component of positive 0.940. That would be 70. So you'd have cosine of 70, sine of 70. So that's 0.342, positive 0.940. And now your y component in the new coordinate system would be this vector expressed in the old coordinate system dotted with your new y-axis. So in a way, I think that's kind of a more like intuitive way to do this, but you can also do it more quickly with a rotation matrix, and you'll see when you set up the rotation matrix that what you're doing is these exact same calculations. So the second way is a rotation matrix. So if we want to go from this to this, what we're doing is rotating clockwise 20 degrees. So our theta is negative 20. So our vector in the new coordinate system, yes, thank you. So our vector expressed in the new coordinate system is cosine of negative 20, sine of negative 20, negative sine, negative 20, cosine of negative 20, times that vector in the old coordinate system. And what this does is it gives you, so the x component of what you're looking for is this vector dotted with cosine negative 20, sine of negative 20. Your y component is the dot product of sine, negative sine negative 20, so sine 20, cosine negative 20, and it's the exact, obviously the answers have to match, so it's the exact same thing we did in the first method. Right. To go from your original to the new, how do you have to rotate it? And this is the 2D version. Are you taking deform right now? I can't remember. Yeah. So in deform, we have to do it all 3D. But so in 2D, all your rotations are about the z-axis. But in 3D, obviously, would be a version of this for about the x-axis, the y-axis, the z-axis. You just have a 3x3 instead of a 2x2. Any other questions about that one? Not on the exam, that's right. I think there is a part where I go into this in more detail. I used to go into this in more detail later on, but I'm actually replacing that part. So I don't think we're using this at all in this class. But the set, right, not even then, because we're always going to have our coordinate systems instantaneously aligned. Just one's moving and one's still, you know. But in a way, I think that's sort of sad because because dynamics is where this gets used the most, you know. But it's not necessary for like understanding the ideas. But if you're really doing dynamics calculations, you're tracking. The reason we don't have to use it is because we're doing calculations at a single instant. So we can always at that instant have our rotating coordinate system line up with our stationary coordinate system. But if you're trying to track something over time, say you're writing a computer program to track like something about this satellite or whatever, if you have a stationary coordinate system, there's one instant where the rotating one can match up with your stationary one. All the other ones you're going to have to do this, use this rotation matrix to. It's a little hard probably to. You can maybe get sort of a vague sense of what I'm talking about, but in dynamics you have to use this stuff all the time if you're doing real dynamics where you're writing a program where at each instant you're tracking something, calculating something. But we can do this class without it, just looking at one instant in each problem, you know, so that's how we do it. Yes? That's a good question. Well, yes, to get ready for, so I would say as far as getting ready for the test or whatever, your first job is to make sure that you understand the ideas in the homework problems. But yes, as like a way to solidify these ideas, I really like that thought. There's probably a way you could set up a linkage that involved
At this position, we'll function of time,
velocity and acceleration.
there's a chain dangling from the attachment with the mass of this. I can make it a problem for you.
I hope we're not giving you test questions.
No, I'm not really that way. It's not really my thing, but
This is one problem, but it's hugely terrible.
some people like doing that. That's not really my way, I don't think. Not on purpose. Yeah.
Never been in a bad mood designing a test. I'm gonna make all these guys fail.
Then I'm gonna give them a second chance.
Yeah. Well, I've done that. I've done that. But I've made up examples that, you know, like it's easy to make up a problem if you haven't gone through it yet, and and it has, you don't realize it has a middle thing you have to do that you hadn't thought of that's hard, whatever. But yes, I have done that for sure. Okay, so you could do a problem like this where you have a linkage and this is rolling without slipping, and you prescribe some of the accelerations. Oh, I meant this to be at the top, not at the middle. The middle's like a cop-out. Okay, how about that? Well, and you could use what you know about, say the motion of the wheel to figure out what the acceleration of that point is. You could do something like that. That would involve rolling without slipping, circular motion, relative motion. We could do something like that. Well, I'll take homework questions, but if we run out of stuff, I could do some problem like that. That's a good idea. No. Yes. Yeah. Oh, yeah. Yeah, it's just totally the tangential is one term and the centripetal is the other term. That's true. Yeah, so this is the centripetal acceleration. Notice that all of these, so normally in the cross product, when you use cross products, you're getting something that is doesn't usually not have the magnitude of all the things multiplied together, but in this case, these are all mutually perpendicular. And so this always has a magnitude of omega squared r. And the cross products just make it point towards the center. And same thing here. These are always perpendicular to each other. So this always has a magnitude of alpha r. And the cross products just make it point in the correct direction. And so when you did physics, at least most of the problems you did, I'm sure you calculated your centripetal acceleration magnitude this way, tangential acceleration magnitude this way, and then you just had to sort of think about like, okay, it's going this way or that way. But this does it for you, so no thinking, which is ideal. Yeah, I do too. It saves brain space for. Yeah. Right. Video games, yeah. Any other questions about that? Does that make sense, Richard? Yes. Any other homework questions? Yes. Yeah, sure. Mm-hmm. If you have a okay, so like let's say this is just some surface, and you have a vector let's say your vector is this. That's your vector u. If you come up with a unit vector in the direction of the wall, okay, so this is This is just some unit vector. What am I going to call this? Let me call this one U hat. So that's a unit vector, and let me call this one V. Okay. Then V dot U, which is the same thing as U dot V, is a projection of that vector onto that wall. This has to be a unit vector. The unit vector part is important, but that will tell you, that will give you exactly a vector in the direction of this. So it would give you, I don't know, that's not the best picture probably, but that's sort of what it does. It's if you take a dot product of any vector with any unit vector, it will give you the projection of that vector onto the direction of the unit vector. Well, that's what, yeah, yeah. Yes. And then you would, and then if you wanted it to be a vector, you take that scalar and multiply it by this.
Oh, that's where I was.
Okay. Any other questions? I'm erasing this. I don't like it.
Reminder.
Okay. Oh yeah, the quiz, right. Good thinking.